Okay, this is Physics 1C for May 6th. Today we're going to look at some applications of Faraday's law, starting with this problem right here. Okay, so last time we learned about Faraday's law, and just to refresh your minds on what that was, we said that Faraday's law says that you can have an EMF induced in a wire as long as there is a change in magnetic flux over time. So we're going to look at 3 examples of problems that we can solve that involve this. So here's the first one, the slide wire generator. This shows up in basically all, pretty much every physics textbook that covers Faraday's law uses this example. It's a really good example. And so, yeah. Okay, so it says we have a U-shaped conductor. So that's this long bar here, and then this short bar here, and this long bar here. So that's all one conductor. And then we have another conducting rail that is connected to it, or just another conducting bar that's connected to it. And this bar is free to slide left and right. And the bar is being pulled to the right with a constant velocity. And the entire system is embedded into a magnetic field, B, that points into the page as represented by these X's that are shown here. The length of the bar here is L. So it says, we lay a metal rod with length L across the 2 arms of the conductor, forming a circuit, and move it to the right with a constant velocity V. This induces an EMF and a current, which is why it's called the slide wire generator. Find the magnitude and the direction of the resulting induced EMF. And we're going to do some other things. We're going to find the force needed to pull it at this rate, the power generated, and we'll say if we know what the resistance is, we can try to find the current in the system too. Okay, so let's focus first on finding the EMF. So we need to use Faraday's law. And we have a system where, sorry, there's like a piece of apple stuck in my teeth. We have a system where we have this closed loop right here, and the bar is being pulled to the right. So what's happening to the magnetic flux through this loop as the bar is pulled to the right? Is it increasing or decreasing?
Decreasing.
Did you say increasing?
Oh, no, increasing. Increasing, yeah.
Okay, and what's making it increase in this case?
The moving thing.
And that's what portion of our calculation for flux is that making it get bigger?
The area.
The area. Exactly. Okay. So let's write our equation down in a simpler way. So there's only one turn of wire here, so this is just going to be negative ddt, and then I'm going to write, for the flux, I'll write BA cosine of theta, where theta is the angle between the magnetic fields and the area vector. As you can see in this picture, they've already drawn the area vector in here. That's what the cross is right here. So the angle between those two is going to be 0, because the B is in the page and the area vector is also into the page. Because the flux is increasing, we can use Lenz's law to say that means that the current has to flow around in this direction here. Because what we found from Faraday's law, from Lenz's law last time, is that when the flux increases, that means that the direction of the current needs to have an induced magnetic field that's opposite to the external field. So if the induced magnetic field comes outwards, that's going to give you a current that flows as they show right here. So that's the current direction. All right. So of these things that are in this equation right here, then, we can pull the magnetic field out, and we just have to deal with the rate of change of the area. That's what's going to control how much induced EMF we get in this problem, is the rate of change of the area right here. So to figure out how fast the area is changing, what I'm going to do is I'm going to say, let's label the coordinate of our bar right here to be x. So it starts off and it's just this x right here, and the bar is moving to the right. So I would say that at any moment in time, so here, just to be really clear, this is like the x coordinate at some later time. So we'll call this one x prime. So it starts off at some coordinate that we call x down here. We don't know how long it is. And later on it's at some coordinate that I'm calling x prime. So if x represents the location of this bar, then we could say that the area of our loop at any given time would be equal to what? The area is a rectangle, right? So one side is L, and if the other side is x, it would just be L times x, right? So we plug that into this equation. Then we can say that the length of this wire is constant. So we're left with b times L, and then what's left in this equation is just dx dt. And if x represents the position of the bar at any moment in time, then dx dt is going to be equal to the velocity. Right? And this is our answer. A really nice, simple answer. This is sometimes referred to as motional EMF, because this same type of expression is going to show up really more than once. And of course, the negative sign is really just there to represent the direction of the EMF. And I think in problems like this, it makes sense to just write it as just the absolute value. But there we go. Anyone have any questions? So let's add one other thing into this. Let's add a resistor into our system. So I'm going to put a resistor over here. And let's say that the bar and the U-shaped bar and the rail here that's going across it, let's say they have negligible resistance compared to this resistor over here. And let's figure out the following, let's answer the following question. So this is going to be kind of like part B. We're going to find what is the current flowing. We want to find the power dissipated by the resistor. We want to find the force needed to pull the bar. And the last thing is going to be, we're going to find the kind of like applied power, I guess. Or maybe a better way to put it would be input power. That is to say, what's the rate at which this force needs to use energy in order to keep pulling this bar, basically, if that makes sense. I think this answer, what I'm asking here, will make more sense when we get there, after we've answered these other three. Okay, how do I find the current? This part's easy.
EMF over R.
Yeah, so to find the current, we just take this EMF that we have right here. The current is going to be equal to E divided by R. So this is going to be B times L times V divided by R. Okay, that's easy. So that's our current. The power dissipated by the resistor. How could I calculate that?
We could use a P equals IV, or no, in this case it would be
I squared R. Does that work? Same thing,
yeah,
right?
That's fine.
Yeah. So we could either take I times E or I squared R. It doesn't really matter. You get the exact same answer. Maybe in this case it's actually easier to do I times E because here's E and here's I. So let's just do that. Let's do the way that you said. So if I take I times E, I'm going to get, well, they both have B, L, and V. So you're going to get B squared, L squared, V squared, and then we have an R in the denominator. Okay, so this is the power dissipated by the resistor. So let's call it piso R or something like that. B squared L squared V squared over R. Okay. Next, let's figure out the force needed to pull the bar. All right. How can we do that?
Use the
For
equation.
this is for a constant velocity.
Magnetic force.
It's moving with constant velocity. What about magnetic force? What were you saying?
Like the equation where we had like V cross B for magnetic force. Can we use that?
The IL cross B, so you're thinking of this one. F sub B is equal to current times L cross B.
Mm-hmm.
We are going to use that. So our current, here, let's use purple because that's what they're using. So our current's going this way, right? Okay. And if the current goes up, then what's the direction of this magnetic force then? If you do L cross B. Just on this piece right here. What's the direction of the force on that piece?
Is going to towards the left.
Yeah, to the left.
Yeah, because you go I cross B, your thumb points left, right? Okay, so let's draw a vector for that in here. So the force on the wire is going to point back like this. Let's make it red. So this is going to be the magnetic force. And it almost has to point to the left, right? Because if it pointed to the right, then this bar right here would accelerate, right? Which would be kind of stupid. FB, or just kind of like, it'd be like free energy. Okay, so FB is pointing to the left. All right. Now we need to have a force applied in the opposite direction to counterbalance that then, right? Or else the object isn't going to keep going forwards. So that's the force we want to calculate, is what is the, we'll call it the applied force. We want to calculate what that's equal to. We're also going to assume that there's no friction forces. There could easily be friction forces here and here, and we can do a problem like that too, but for this one, we're just going to assume there's no friction. So the applied force just has to be big enough to overcome the magnetic force, and if it is, then it will automatically make the bar move at a constant velocity, right? Because then the net force will be 0, so the bar can move at a constant speed. Okay, so to calculate this then, we just say net force is equal to 0, so FB has to be equal to F applied. FB is ILB, right? So it's I, which is this, divided by R. That's I times L, and then times B again. So that should be equal to the applied force. And so it's going to be B squared L squared V divided by R. Does that make sense?
Yeah.
Okay. So the last thing we want to do is to calculate the applied power or the input power. That basically means take this applied force and figure out the rate at which it's delivering energy to the system. Okay? How could I do that? How could I calculate that? What's the easiest way to find the power input by this force here?
Trying to think back to like when wasn't it like F times V?
Yeah, that's it. The power is equal to F dot V. And since the force and the velocity in this case are in the same direction, we're using the applied force here. It's just going to be this, B squared L squared V squared divided by R. you'll notice that this is the same as this, right? Which means
Sure.
in this system, what's happening is that the input power is exactly equal to the output power. Which is a little bit kind of ridiculous. It's kind of ideal. You'd have to have some kind of losses in the system due to friction. But it is kind of nice that, you know, without considering those losses, you get an exact kind of conversion from what you're putting in to what you're getting out. That's kind of cool. And we got the answer two different ways too, right? One of the answers we got by using the definition of power through a resistor, which is current times voltage. And the other one we got by taking the force and multiplying by the velocity, and we calculated the force by using the magnetic force equation. So we kind of used several different topics of 1A and 1C to get to these two answers. Okay, does anyone have any questions about this problem? You're going to see a few different problems in your homework that look like this, or variations of this type of thing. Okay, the next application we want to look at is this problem right here. I think for this one I'm going to give you some time to actually try to work it out on your own. So let's read through it and look at what's happening though. So here's our picture. So it says, an aluminum ring with a radius R1 is equal to 5 centimeters and a resistance of 3 times 10 to the negative 4 ohms is placed around one end of a long air core solenoid with 1,000 turns per meter and a radius of 3 centimeters. Okay, so this is the ring with a radius of 5 centimeters and a resistance of 3 times 10 to the negative 4 ohms. And then the long air core solenoid is obviously this thing with all these coils that are drawn around it. The solenoid has 1,000 turns per meter with a radius of 3 centimeters. We're going to assume that the axial component of the field produced by the solenoid is 1/2 as strong over the area of the end of the solenoid as at the center of the solenoid. So basically, just to remind you, the magnetic field produced by a solenoid we derived in the last chapter was equal to mu naught times the number of turns per unit length multiplied by the current flowing through the solenoid. It's a really simple expression. So in this case, the magnetic field that we're going to use, it's saying that over the end cap right here, that this magnetic field has half of that value. So we're just going to divide this by 2. That's going to be our magnetic field in this problem, because it says 1/2 as strong. Also assume that the solenoid produces negligible field outside its cross-sectional area, so that would mean anywhere outside of the cross-sectional area, the field's going to be 0. And then we know that the current in the solenoid is decreasing at a rate of 270 amps per second. So I'm going to call that di dt, the rate of change of the current, and it is a negative 270 amp per second in this problem.
It should be positive.
Oh, it says increasing. I thought it said decreasing. Thanks. Okay, yeah. A says, what is the induced current in the ring? And then it says, at the center of the ring, what are the magnitude and direction of the magnetic field produced by the induced current in the ring? So take like 5 minutes and try to solve this if you can. Or at least try to set it up. Okay. Is that enough time? Were you all able to figure this out? Probably not, right?
I
Think so?
I think so.
Yeah.
Oh, really? Okay. All right. Well, let's try to go through it. Okay. So, given all this information, we might as well write some of these pieces of information down over here so we can use them. So R1 is 0.05 meters. R2 is 0.03 meters. We got the rate of change. The number of turns per unit length is 1,000. It says right here, 1,000 turns per meter. So it's 1,000 inverse meters. And the resistance of the ring, the outer ring, is 3 times 10 to the negative 4 ohms. And that's it, right? First part is, what is the induced current in the ring? So we obviously want to use Faraday's law. And to find current, we basically just take it, divide it by the resistance. So this is going to be negative N, where N is the number of turns in the thing that's having the EMF induced in it. So that's going to be the gold ring right here. And then times d phi dt. And I'm just going to go ahead and, instead of writing phi, I'm just going to write it as BA cosine theta again. And we have to divide all of that by resistance now to get to current, right? Now the number of turns in the gold ring, what is that going to be?
Just one.
1.
Okay. So we have just negative d dt. Theta is going to be the angle between the magnetic field and the area vector. The magnetic field points which way in this problem? The magnetic field of the solenoid, I should say.
Towards the right.
To the right, that's
Right.
So let's draw that on the picture right here. So the magnetic field of the solenoid is going this way. And that's going to be the magnetic field that shows up in this equation here, right?
Mm-hmm.
The areas are not changing in this problem, right? So we can pull the area out. So we have the area multiplied by ddt of the magnetic field, but it's the magnetic field of the solenoid, which is this right here, right? So plugging all that in there. Okay, so now for the parts of the problem that are a little bit tricky, I suppose. I don't know if it's tricky or not. So what area do I use for this? We were talking about the flux, and it's the flux through the golden ring that we care about, right? But what area are we going to use?
We would use the big ring, the gold rings area.
Mm-hmm.
Does
It'd be
everyone agree
pi
with that?
r1 squared.
So you think that the area we want to use here is pi times r1 squared. Okay, does everybody agree with that?
Don't you use R2 or?
What would be the reason for using R2? So this is our scenario. If we look at the end, we have 2 radii, right? This is R2, this is R1, and this is R2. Now, where's the magnetic field located in this problem? It's located in here, right? I thought I clicked on the green one, but it didn't click. There it goes. The magnetic field is in the inner ring only, right?
Yeah.
So if we're talking about flux through this bigger ring right here, there is no magnetic field in this outer region here, which means all of the flux has to come from just the center right here. Does that make sense?
Gotcha, yeah.
So instead of using R1, we're actually going to use R2 here, the smaller radius, R2. Because there is no magnetic field. That specifically says, if we go back and look at it, also assume the solenoid produces negligible field outside its cross-sectional area. So the whole reason of doing this problem is just to indicate that there are going to be problems where it's not super clear which area you should use, and if the thing that you're having if the thing that has having the induced current in it, you're not always just going to use the area of that object. You're going to use the place where the magnetic field is, basically, to get the flux, right? Does that make sense to everyone?
So it's only the area that the magnetic field goes through.
Yeah, exactly.
Okay.
Oh, this reminds me. There was a problem we did yesterday, and we didn't do one of the parts of it, and it's kind of related to what we're talking about. So I'm going to go back, and we'll follow back up on that in just a second here. Okay, so now we know what we need to put into here. Of all the things that show up in the derivative, mu naught, n, and 2 are obviously all constants. We can pull those out. So we said a was going to become pi times r2 squared. And then we have mu naught, little n, di dt. All of this divided by 2 times r. And now we should be able to calculate all this. Okay, R2 was 0.03. Mu naught is 4 pi. Little n is 1,000 inverse meters. di dt is 270. And we're dividing all of this by 2 times the resistance. And that should be the current. Can you all calculate that for me? I left my phone in the other room.
Y'all get like 4.8 times 10 to the negative fourth. Or negative, I guess.
I probably did it wrong then.
Oh wait, no, that's the EMF. Yeah, sorry. The current would be 1.6.
Yeah, that's what I got. 1.6.
Yeah, 1.6.
Just 1.6 amps or 1.6 times 10 to the minus 4?
Just 1.6.
Just 1.6.
Yeah, I got that too.
Oh, you were talking about the EMF, I guess.
Yeah.
Okay, so the current ends up being 1.6 amps. Okay, any questions about that?
I just want to clarify, when we do like Faraday's law, and we focus on whichever object we want to calculate the flux through, correct?
You focus on the object that you want to calculate the flux through, is that what you said?
Mm-hmm.
Yeah.
Okay.
But it's tricky because there's going to be problems like this one where the whole object doesn't have flux through it. It's only like the center of the object that has the flux through it, right?
Yeah.
Okay. It's the whole point of doing this particular problem is it highlights this problem, and we'll see this show up in a lot of different areas too. Okay, so next thing to do is to find the magnitude and direction of the magnetic field produced by the induced current in the ring. Okay, so this was part A. For part B, I'll just write that over here. We just want to find the magnetic field of the ring, and we have an equation for that. When you have a ring, I believe the magnetic field that we get is mu naught times the current in the ring divided by, I think it's just 2 times the radius, which in this case is R1, right? I think this is the equation. Does that look right to everybody?
I think so, yeah.
I'm checking.
You can look in your notes or the book if you want to. Pretty sure that's the right answer. By the way, I was looking at these units. Does it actually work out right? Let's see. This meter cancels out with this meter. This amp cancels out with this amp. And we have Tesla meters squared per second, which is volts. Yeah, okay. Times current. We just found the current was 1.6 amps. And then we just divide by 2 times R1, which is 0.05. And you all can tell me what this is equal to. And then what's the direction going to be?
To the left.
Left.
Yep.
I get 2 times 10 to the power of -5.
Seems about right. You all agree?
Yep.
Okay.
Mhm.
All right, we're going to do one more problem, but I want to go back to something from yesterday because I forgot to talk about it. So we did this problem here. Right here. And part B is what we didn't do. So just to remind you, in this problem what we had was a north pole of a magnet here, a south pole of a magnet here, and there was a wire inside of it. And then you had a magnetic field from the external magnet that was changing at a rate of 0.02 teslas per second. We found the induced EMF and the induced current in the circuit, and the induced EMF we got was negative 2.4 times 10 to the negative 4 volts. And this was the current that we got, which we got basically by taking the induced EMF, right, and just dividing by the resistance. Part B, which we didn't answer, says, if the loop is replaced by one made of an insulator, what effect does this have on the induced EMF and the induced current? So it says basically, instead of using a wire right here that's made of metal or conductor, if we replace the loop with just an insulator, maybe like a ring of plastic or something like that, what effect does this have on the induced EMF and the induced current? What do you all think? Take it one at a time. Is the induced EMF going to change if we replace that wire with an insulator? With a basically insulating wire that just doesn't have metal inside of it. Put a piece of rope in there. Is it going to change the induced EMF?
I'd say no.
Nothing seems obvious that it would.
Yeah, it doesn't, right? Because the induced EMF is given by all the factors that are shown there. You know, it's 0.012 the area times the rate of change of the magnetic field. So the induced EMF is still going to be there, right?
Mhm.
So that's important to understand that, like, there is an induced EMF even if there isn't a wire there to, like, generate a current, right? Because if what effect would that have on the induced current then? The EMF is the same, but what's going to happen to the induced current?
I would say to go to 0
Yeah, it's going to be really small. And why is that?
because an insulator.
Resistance.
Insulator.
It's an insulator, so the resistance is going to be extremely high. Yeah, maybe it's like 5 million ohms. It's going to be actually much more than that. So there may be a very tiny amount of current that tries to flow through it, but it just isn't going to be able to because the electrons just don't move as freely, right? Okay, so that's just something to think about. The EMF is there even if there's nothing to, you know, make current flow. You know what I mean? The EMF is automatically there. Now there's something we can say that goes beyond that, which is, you know, if there's an EMF there, I mean, it's everywhere too, right? If you think about it, like, just because I put one loop right here doesn't mean that there's not an EMF induced like in the air, you know, a centimeter above it, right? There's still an EMF. And really what that means is there's actually going to be kind of an electric field that's produced that points similar to the way that the EMF produces. Okay? And that's something we're going to end up talking about next week, but it's kind of a hint at how changing magnetic flux can produce electric fields. Okay, I was going to do this problem, and it is relevant, and maybe we can, but I actually realized that there's a type of problem you're going to see show up. It's either going to show up on your homework or it's going to show up in the lab manual. I know it shows up in the lab manual, and it very likely might show up on your final. So I'm just gonna kind of create a problem along the lines of what I'm thinking about. So here's what we have to do to make this kind of problem. It's really easy to construct. So we start off with a wire, and this is going to be a long, like basically infinite wire that carries current. Okay. So we have a current flowing here, I, but this current I is going to be equal to, let's see, we can use really any function we want here. It doesn't really matter what we use. We'll probably use a, I don't really want to do a cosine function. Do I? Let's just use an exponential decaying function. Okay, so our current is going to be I naught times e to the negative. What do I need? What kind of coefficient do I need to put on this? Can I just put e to the negative
X
t?
KT.
T.
I'm trying to think if I need to put a constant on
Okay.
here. I do, right?
Mm-hmm.
Because otherwise the units won't make any sense. Because the exponential function has to have units of 0, or has to have units that are dimensionless. So we'll have e to the negative kt. So that's going to be our current, and then this will just be, we'll call it I sub naught, okay? And we can pick values for these things if we decide later on that we want to get numbers, but it's not going to be super important. So the point is that we have a current in this wire that's exponentially decaying, okay? That's what's going on, okay? Now next to this, we're going to place a loop, and let's give it some parameters. So we'll say that the distance that the loop is away is going to be a. So this is going to be the distance that the loop is away from the wire. And then we'll just use b and c for the other dimensions. So we're going to call this side c and this side b. Can we use L and W? Maybe we just use L and W. Is that going to cause a problem? I don't think so. That way it's length and width. So this would be the width, right? And this would be the length. Okay, so those are our dimensions to our loop. This is going to be a loop of conducting, it's going to be a conducting loop. And what we want to do now is basically just find the EMF induced in the loop. Pretty simple. Okay, does everyone understand the problem?
Mm-hmm.
Okay, first thing to do when we're finding induced EMF, because we know that we want to apply Faraday's law, is we're going to need to calculate or find some way to calculate the flux through this loop over here. So let's start off by drawing the direction of the magnetic field inside the loop. What is the direction, if the current is flowing upwards, what's the direction of the magnetic field inside of this loop right here?
Into the page. Into the page.
Yeah. And in addition, it's not uniform, right?
True.
So on the left side of the loop, it's going to be bigger, which I'll use these bigger x's to represent. And as we move across the loop, it's going to get just a little bit smaller. And that's because the farther away that we get from our wire, the smaller the magnetic field is going to be getting. Okay, I kind of overdid this. So now I can't really even make the x small enough. But anyway, that's the direction of your magnetic field now, okay? And of course, it's also out here too, right? The magnetic field's also in this region as well. This reminds me of playing dominoes. Okay, So there we go. So that's the direction of the magnetic field. It is getting weaker. Because it's an infinitely long wire, we know what the magnetic field that it produces is. That magnetic field is going to be equal to mu naught times the current divided by 2 pi r, where r represents the distance away from the wire, right? So that's why I'm saying that it's getting weaker as we move to the right. Okay. Now, how do we calculate the flux now? Normally we would just do B times A, which would be B times L times W, right? And that is what we're going to do. But because the flux is not the same throughout this entire object here, it's not that simple. I can't just take B and multiply times L times W. And why not? Well, because the B at this location is not the same as the B over here, right? So how can we do that? How can we actually just calculate what the flux through the loop is? This could be a problem in and of itself. Even without Faraday's law, the problem could just state, well, what is the flux through the loop equal to? That by itself is a hard enough problem. And probably the hardest part of this problem. How do I do that? How can I calculate the magnetic flux through my loop?
I'll say an integral.
Yeah, we have to integrate. So flux is defined as the surface integral of B dot dA. So we're going to need a dA. And we're going to need probably to find a dA, to make things simple, that is a place where the magnetic field is uniform. So, much like we've done in the past, we're going to break our object up into slices that we'll call dA. So this is going to be like one slice that we cut out of our object here. I almost did it. It's so weird that these things, like, after you take your pen off the paper, it like reorients the thing. Oh my god, is it not going to like make it smaller? Okay, there we go. Oh, it's because I'm not touching the edge. I want to touch this one. There we go. That way. That way. Okay. So now we're going to... That's going to be our cut. Okay. We're going to try to find the flux through this little strip right here. And we're going to say that the strip has dimension that we're going to call dA. I'm going to leave this part. No, I can... I'll just kind of write it off to the side. So this is going to have... That's our dA right there. And because the flux is decreasing, I'm going to say our dA vector is going to point into the page. All right. And then we need to use some kind of a variable, right? So let's define... I was wondering if we could define the left edge of this to be 0, but I don't think we can really do that. So we're going to call this point to be x equal to 0, and we're going to drop a coordinate system on here. Well, part of a coordinate system, because we're only going to need one direction. So we're going to call this the positive x direction, which means that this point right here is going to be x equal to 0. Okay.
Yes, sir.
What's up?
I had a question. So you said because flux is decreasing, our area vector points into the page. Can you explain that one more time?
Sure. It's just, you know, it doesn't actually matter that much.
You can just take magnitude.
Yeah, I mean, the thing is that
But I get
the
it.
reason why I chose the area vector to point in is because the area vector needs to be consistent with, like, the current direction. So let's just I left that part out. This question would be super easy to answer if I had just already written this on here. What direction is the induced current in my loop going to be in this case? Oh, I really need to sneeze. I'm so glad that happened. This whole class
in
I'm trying
the
to...
direction.
The same direction, right?
Yeah, yeah.
Okay, so the induced current is going to go like this. No, the other way, right? Sorry. Basically, take your thumb and point it into the page. The induced current has to flow in that way. So this is going to be the direction of the current. This way, and so on. Okay, So looking at that, John, is it clear to see why the area vector needs to point in? Because the area vector has to be consistent with the direction of the current. So does that help?
Yeah, that helps.
Okay. Okay. If the current was increasing over here, if the current was increasing, then I would have made my current go the other way, and the area vector would also go the other way. Okay, so there we go. All right, so like I said, we are going to define this to be the positive x direction. We're going to say that the location of our cut right here, not our cut, but the little piece that we're taking out of this, we're going to say this is the x coordinate right here. So this point is going to be x. So I'm just going to label it this distance is x. Okay, so this is going to be the variable that we're going to do the integration over. Okay. And yep. And now what we can say is, since we've defined what x is, that means that we can define the thickness of our cut. So this is where I would like to have a little bit... okay. I can erase this. I don't need to have this in here. So the thickness is going to be dx. This thickness here is going to be dx. So what's the area dA going to be equal to then? What's the area of this little cut here?
dx
dx
times
times L.
Mm-hmm.
Yeah.
So L dx. And now I think we can do this now. So our flux then is equal to the integral of the magnetic field. The magnetic field is mu naught times the current divided by 2 pi r times dA, which is L dx. The b dot dA just becomes b dA because the magnetic field is into the page and dA is into the page. Now, the current is not a function of x, right? It
True.
could have been, but it is not. Or the magnetic field could have been a function of x, but it isn't in this case. You all will do a problem where it is in your lab manual. So we can pull this whole thing out. What's up?
Isn't that a function of x?
What? The magnetic field?
Yeah.
function t.
Sorry.
The current.
The current isn't. R is. R in our case is actually equal to x. Now that we've redefined it, right? Sorry about that. The magnetic field is. The current is not. That's what I'm trying to say. Sorry about that. Do you see why R would get replaced by x, by the way? R is the distance away from the wire. So that's how far away from the wire we are here, which is just x. Sorry, Cam. Did I confuse you?
No, that's all good.
Does this look right now? Okay, I apologize. I think I said something that was wrong. I think I said the magnetic field does not depend on x, but it does. It's the current that doesn't depend on x. Okay, so we have basically just dx over x now. And since we've gotten rid of the dA, technically, we should probably get rid of one of these. Okay. And then what are my limits on this going to be? We need to integrate across the loop, right?
It would be a to a plus w.
Yep, because we're going to integrate from the left side of the loop to the right side of the loop, which is x equal to a and x equal to a plus w. So there's our equation. So we end up getting mu naught I L over 2 pi. And then what's this integral going to give us?
The natural log of x.
Yep, natural log of x. And then we just plug our limits in, a plus w over a. Right? Kind of skipped a step there, but are you all okay with that?
Yeah, that's fine.
So that's the flux. So we're kind of halfway done with the problem. Probably done with the hard part, I suppose. So now we just need to plug it into our EMF equation over here. So if we do that, we're going to get EMF is going to be equal to -1 times ddt of all of this junk right here. So it's ddt of shouldn't have written it at such an angle. There we go. It's ddt of all of this I'm gonna move this. Oops, didn't mean to do that. Move this down here. Okay, so it's ddt of all of this. So we need to pull out anything that doesn't have a time in it, right? Which is going to be everything except for I. So we have mu naught L over 2 pi natural log of a plus w over a. And then just di dt, right? So now, there's a negative sign still. This negative sign is going to go away, though. Now we just need to do di dt. So the derivative of this is just going to be negative k I naught e to the negative k kt. So we'll have negative mu naught L over 2 pi natural log of a plus w over a. And then di dt is going to be negative k I naught e to the negative kt. And that is basically our answer. We're going to have one more line here, but that's pretty much the answer. So our final answer then is going to be, these negatives cancel out, so we're going to have mu naught L k I naught divided by 2 pi natural log of a plus w over a. And then there's the EMF actually depends on time now. It's now a function of time. And assuming I didn't drop any of the factors there, which would be pretty easy to do, should be the final answer. Does it look like I dropped anything?
No, that looks all good.
Okay. And we can obviously pick numbers for all this stuff, but I know for a fact that at least the lab manual version of the problem like this that you're going to see, it doesn't have numbers in it. It's kind of just like this. And there's two different lab manual problems that are similar to this. There's one that looks almost exactly like this, where you have a current flowing up and then you have a loop. The difference is that the problem in the lab manual, the current is constant, but the loop is being pulled to the right, kind of similar to what we did in the first problem. The loop is being pulled to the right at a constant speed. So you have to do all the same stuff that we did for finding the flux. But then the difference is that the x-coordinate of the left portion right here is moving in time. Right? The left edge of this thing is going to be moving to the right. So it's going to make it change some of these things that you do here. But I think the flux calculation is going to be the same. It's just that I believe this thing right here that I called A, when you do your lab manual thing, so try to keep this in mind because it will save you a lot of time. When you do this in the lab manual, I'm not completely certain, but I'm reasonably certain that you're going to get something very similar to this for your flux calculation. You basically, it's the same type of argument. You'll need to show all these steps, and on your picture, you'll need to show what you did and stuff like that. But I'm pretty sure you'll get the exact same answer. And the difference will be that A now is going to be a variable, but it's going to be changing at a constant rate because the loop is going to be moving to the right at a constant speed. So usually what students do is they replace A. Okay, I should slow down. I'm just sitting here describing a problem you haven't even looked at yet. And I'm trying to help you, and I know this is all being recorded, so you can always come back and look at it, but I don't know if anybody will. So I'll just slow down for a second. Do you all understand what I'm saying?
Yeah, it is easy kind of to visualize. Yeah.
Okay. It's hard to visualize, but take the exact same problem, right? I don't remember what's going on with the current. I think the current in the problem you have is just a constant number. I'm pretty sure it's just a constant number. And the time variation occurs because the loop moves. So I'm pretty sure all you have to do is just in this equation, you're going to replace A with V times T because the thing is going to be moving at a constant velocity. And if you replace, I think if you just replace A with V times T, then when you go to do the EMF portion of it, right, you have to take the derivative now. So you'll be taking the derivative of the natural log of this thing that will also have a velocity inside of it. So you'll need to do some chain rule stuff. But the general kind of like approach is going to be about the same. So I hope that helps, because that problem can be really tricky. You have another problem where time to stop. But there's another problem where you need to do a flux calculation. I was going to say where the magnetic field is a function of x and time. But that problem is actually pretty easy. People usually don't have any problem with it. And then I think you have a homework problem on mastering physics that looks like this too. So anyway, I just wanted to kind of cover as much as I could today to help prepare you to be able to do those problems, you know, and just set you up to be able to succeed without having to do the normal thing with physics where you just take forever to figure something out, right? So I think that's it for today. I don't know what time it is, but it's probably about an hour, right? Yep, right at an hour.
3:06.
So we're going to stop the recording, and I'll answer any questions that you all have.